Hello guys, this video is an adjoint operator T star of T. First we discuss the criterion for the existence of adjoint operator T star. Let x and y be normal spaces and T be an operator from x to y which is bounded and linear. So this is the criterion for the existence. If T is bounded and linear, then its adjoint operator T star exists, which is defined from dual of y to dual of x. Now let me give a short proof of this criterion. First, since x and y are normal spaces, their dual spaces x dash and y dash exist. Second, for every g belongs to the dual of y, the composition g or t, so which is from the space x to k, where k is the field of scalar, this composition is well defined. And also, since g and t both are linear and bounded, this composition GOT is also linear and bounded, which is defined from x to k. So GOT, this composition, it belongs to x dash. So GOT equals to f for some f belongs to x dash. And this defines a map T star, which is from y dash to x dash, such that T star g equals to f. So this gives the existence of adjoint operator of T. Second, we have a theorem which gives a property of the adjoint operator T star. It states if T star is the adjoint operator of T, then T star is also linear and bounded, and norm of T star and norm of T are equal. Now let us move to the proof. First, we prove the linearity of T. For that, suppose G1 and G2 are any two elements of y dash and alpha and beta are any scalars, then since y dash is a vector space, the linear combination of G1 and G2 also belongs to y dash. Now T star times alpha G1 plus beta G2 of x is equals to, we have got this relation from the definition of T star. Now since y dash is a vector space, distributive property, we apply distributive property, we distribute Tx to G1 and G2. Then again, since y dash is a vector space, we apply this associative law and we get this step alpha and beta. Finally, we use the definition of T star and we get this step, and finally we get T star of alpha G1 beta G2 equals to alpha T star G1 plus beta T star G2. This shows T star is linear. T star, linearity of T star. Yeah, okay, हल्का correct गर्नुपर्ने रहेछ. Linearity of T star. Next we show boundedness of T star. We have T star G equals to f from definition. So norm of T star G equals to norm of f, which is the supremum of absolute value of fx. Norm of x equals to 1. Now from earlier definition, f is composition of g and t. So we substitute the value. We use the property of norm, which is greater or equals to norm of g, norm of t, norm of x. We have norm of x equals to 1. So we get this step. Now applying supremum, we get this step. This shows T star G. Norm of T star G is lesser or equals to norm of T, norm of G, where T is a norm of T is a constant. Since T is bounded, norm of T is less than infinity. So we have this form, Tx is lesser or equals to C times x. This shows T star is a bounded operator because this norm, this relation is of the form this one, which gives the boundedness of T star. Finally, we show the norm of T star and norm of T are equal. First, we show norm of T star is greater or equals to norm of T. We have norm of T, definition, supremum, x not equals to 0, Tx upon norm of x. Here we apply the application of Hahn-Banach theorem. Hahn-Banach theorem, important. Here since we have, suppose x not equals to 0, we have tx is also not equals to 0. This relation is important. Since x not equals to 0, tx is also not equals to 0. Then by application of Hahn-Banach theorem, there exists a functional g on y dash such that g of this tx equals to norm of tx and norm of g equals to 1. This is from the application of Hahn-Banach theorem. Now we apply this theorem, we substitute the value here. We have got norm of tx equals to this one, gtx. Then we apply the relation of adjoint operator, gtx equals to adjoint operator t star gx. Then we apply the property of norm, which gives norm of t, norm of g, norm of x upon norm of x. Simplification, since norm of g equals to 1, we get norm of t star. This shows norm of t is lesser or equals to norm of t star. That means norm of t star is greater or equals to norm of t. Next, from the boundedness of t star, we have norm of t star is lesser or equals to norm of t, norm of g, which we derived earlier. Then from the definition of norm of t star, which is the supremum on g, we take supremum on g. Taking supremum on g, we get this relation, t star is lesser or equals to norm of t star is lesser or equals to norm of t. Combining 2 and 3, we get norm of t star equals to norm of t. This proves our theorem. Thank you.